So moving along in chapter 16 into 16.7, the potential at one location. So we've talked about delta V. Now we're going to talk about just V, which would be the potential in one location. So just make sure that you note how a problem is written. All right, so as you know, delta V is equal to VB minus VA. And each one of these are the potential at one location. And you can think about the potential at A is the delta V between infinity and the location of interest. All right, so the potential at A is equal to VA minus V infinity. And of course, V infinity is defined to be 0. And we'll see why in a moment there. So basically, from here until infinitum. So let's look at a point charge. We're very familiar with point charges. So the potential at R is equal to VR minus V infinity is equal to negative the integral from infinity to R 1 over 4 pi epsilon naught Q over x squared dx is equal to 1 over 4 pi epsilon naught, not infinity, we'll just do epsilon with a bow on top, Q over x from infinity to R is equal to 1 over 4 pi epsilon naught Q over R. Because, as we would know, Q over infinity is 0. Because anything over infinity is 0. So we can graph our potential, so keeping this in mind, I can do this. All right. So if we graphed the potential, R V, we would see for positive, looks like this. And then for negative, it would look like this. So not unlike the graphs that we saw last semester when we looked at potential energy graphs. So we can see that electric potential just follows along with what we know about potential from mechanics. So if we know the potential at one location, we can find U of the system if we placed a charged particle there. So we can find the potential energy. So UA is equal to Q VA. And we can use this to derive something we've seen before. So UA is equal to Q2 VA is equal to Q2 1 over 4 pi epsilon naught Q1 over R, because that is the potential at A. You can see from here, is equal to 1 over 4 pi epsilon naught Q1 Q2 over R, which is the electric potential energy equation that we saw in Physics 1. But this is a a neater, more elegant way of understanding it. Okay, so let's look at an example. After all, physics is all about elegance. A metal sphere of radius 1.2 meters has a charge of 4.2 times 10 to the minus 2 coulombs. What is the potential at C, 9 meters from the center? Okay, so VC is equal to V sub C minus V infinity is equal to 1 over 4 pi epsilon naught Q 1 over XC minus 1 over infinity. Now, if you are asked a question like this on a test or a quiz, I would expect to see this set up just to show me the understanding. And then in subsequent chapters, you can just use this. So we would get 9 times 10 to the 9 Newton meters squared over Coulomb squared times 4.2 times 10 to the minus 2 coulombs times 1 over 9 meters. And from here, we get 4.2 times 10 to the 7 volts is the potential at 9 meters from the center. And remember that whenever you have a sphere, your R is always from the center. So this may be 1.2, but this is that 9 meter mark. Okay, so moving right along, let's look at how we can calculate potential energy of some of the different shapes that we've been looking at. So that whole divide and conquer approach, yeah, it comes back a lot this semester. And that's actually because that approach is useful in any problem-solving field. And any time you want to model something, so even the models that you've been seeing now of the different viral vectors, they're taking that approach. They are taking their data together and they're trying to add it up in attempts of coming up with an analytical expression. All right, so we'll look at the potential along the axis of a ring. So the ring has charge Q. And we'll treat it as though it's made of point charges. So here is our ring. It's got some different colors going on here. So we'll say it's made of little Q's. So let's say this is the Z-axis going through it. And it's got some radius R. And now, if we're observing here, for each little q, R, if we just use Pythagoras, Z squared plus R squared, square rooted. Okay, so now we can plug that into our potential formula because we have R. So let's just... There we go. So the potential for 1 point charge on the ring, V is equal to 1 over 4 pi epsilon naught little q over the square root of Z squared plus R squared. All right, and now to get the potential of the ring, we need to add those point charges together. So this is going to be the sum 1 over 4 pi epsilon naught Q over Z squared plus R squared. And we can simplify a little bit further. This is equal to 1 over 4 pi epsilon naught, 1 over z squared plus r squared times the sum of little q's. And of course, that is just big Q. Big Q is the sum of all the charges. So V ring is equal to 1 over 4 pi epsilon naught Q over z squared plus r squared. And this isn't the only way that you could find this result. And this was pretty straightforward to determine by just reasoning through the shape. You could find it through integration. By integrating the electric field of a ring. So remember that negative gradient? Yeah. So V of z is equal to minus from infinity to z 1 over 4 pi epsilon naught qz over r squared plus z squared to the 3/2 dz. And so classical, prove this. Find out for yourself. All right, so moving on with our understanding of potential and potential difference, and just to delineate these two concepts a little bit further. So we remember that delta V in a conductor is 0, which does not imply, or does not mean V is equal to 0, only that there's no change. Okay, so let's think about the potential inside of a charged sphere, a charged metal sphere. Charged metal sphere. So it has radius equal to r and charge equal to q. So at any distance, r less than, or sorry, r greater than big R, the potential relative to infinity is just going to act like a point charge. So 1 over 4 pi epsilon naught q over r. And so that is V outside sphere 1 over 4 pi epsilon naught q over r. We've already seen this before. That's not the interesting part. The interesting part is inside. So inside the sphere and outside the sphere, there's an electric field. So E net is not 0. E net is equal to 0. Thus, the potential inside the sphere is 1 over 4 pi epsilon naught q over r everywhere. So everywhere you go within this sphere, whether you are here or here, this is your potential. So now we have shown that E net being equal to 0 does not mean B is equal to 0. So the potential inside of the sphere is non-zero. All right, so let's look at insulators now. They're a little bit of a different beast. All right, we know delta V in a metal and in equilibrium is 0. Okay, so, but with insulators, it's more complicated. So insulators have molecules that polarize. Thus contributing an electric field. Okay, so to think about what this does, let's put an insulator inside of a capacitor. The reason we use capacitors a lot is because they've got very consistent electric fields all the way across, so they're really useful. Also, there are capacitors with insulators inside of them, so we're dealing with some real world objects. All right, so when this field goes across, let's go ahead and draw the field. So E capacitor. The molecules inside of this will polarize. So you'll have this all the way going up and down. I'm not going to draw it because that's just an exercise in poor drawing skills. So you would have the electric field from the plates, and then you would have the electric field from the dipoles, so E dipole, and E net is still going in this direction. It has just been reduced. So the E dipole reduces E plate. So you get a smaller net field. And this is related to the alpha, the dielectric constant, which is the weakening factor. So the insulator weakens the net field by a factor of K, which is the dielectric constant, and it's a material property. So E insulator is equal to E applied. So that would be, in our example, the field from the capacitor, but you could do this with something else, divided by the weakening factor. So for a capacitor, we can do this. E is equal to Q over A divided by epsilon naught. And for a capacitor filled with an insulator, E is equal to Q over A over epsilon naught divided by K. And K is always greater than 1 because polarization weakens E net in the insulator. Okay, so moving along, I'm going to just start a new page here into energy density, which is going to be a concept. We're going to set it up here, but we're really going to come back to it in the later chapters. So I want to give you this concept now because we can actually use capacitors to understand it, but the result that we are about to derive is general. And for now, you could either take my word for it or read ahead, or just realize that the proof of this is coming. So we've thought about electric potential energy as associated with interacting charged particles, but it can also be associated with fields. So electric potential can be associated with fields. So let's think about this. So let's say we had a capacitor. Here it is. So we would know that there would be an electric field pointing towards the negative plate. There'd be an electric field that would be pointing away from the positive plate, giving us an E net in that direction. Now, what if we were to apply a force onto one of the plates to move it? So a force by U, and it's going to move it some delta S. And so that's going to change the field in the capacitor. So the electric field of one plate is Q over A divided by 2 epsilon naught. And the force on one plate from the other is F is equal to Q over A over 2 epsilon naught. And the force to pull it apart must exceed this. Otherwise, you'll be unsuccessful. So you're doing some work on the plate. So the work you do to move a plate is coming up on the next page. Is delta U is equal to work is equal to Q over A 2 epsilon naught times delta S. So if you recall, delta S is how much you're moving it. And this becomes, and on your own, do algebra. Delta U is equal to 1/2 epsilon naught Q over A over epsilon naught squared A delta S. And A delta S is the change in volume. So what we have here is that delta U over the change in volume is equal to 1/2 epsilon naught E squared. This is energy density. In joules per meter squared. And it's stored in a region with an electric field. Of magnitude E for any E. So any electric field has energy density. And we will see that this result is general in later chapters. 1 over epsilon naught E squared with units of joules per meter squared. All right, this wraps up chapter 16. So next up, chapter 17.